Welcome AP Physics Mechanics students. Today's review topic is rotational motion. But as you can see, I've labeled this video Rotational Motion 1. There's another rotational motion video that'll come in the next lesson. And the reason why I split rotational motion into two topics is because basically it's a very large topic. By the time we got to rotational motion, we had studied many units already. We studied forces, the pushes on something or the pulls on something. So we studied a whole unit there. Then we studied a whole unit called kinematics, which was the mathematical description of motion. Formulas for the x-coordinate, the velocity, the acceleration, graphs. That was unit 2. Unit 3, we studied Newton's laws, which put those two units together. Forces produced accelerations, and so we were able to tie those two together when we figured out accelerations of something. Then we went on to energy. We had things like potential energy, kinetic energy, and the law of conservation energy. That was the next unit. And then momentum, collisions, things like that. Even after rotational motion, we studied oscillations. All of those topics are within rotational motion. You can have rotational kinematics, rotational Newton's laws problems, energy, momentum. So as I said, it's like an entire year compressed into one unit. That's why we split it into two videos, okay? But what we're dealing with, instead of things moving like this, we're now dealing with rotations, okay? So all those topics within rotation. As I said at the time, the best strategy, because this is so many topics within this topic, is to sort of piggyback the knowledge, the new knowledge on the old knowledge. So for example, here we have some kinematics definitions, here's some kinematic formulas. You take these ideas and you convert them to rotational motion ideas, the learning will go much quicker. Okay, so for example, with linear motion, we had velocity v. That was how fast something was moving one way or another. It was defined as the derivative of the x-coordinate with respect to time, or if you wanted to find the average velocity, you could do change in x over time. That tells you the meters per second that something is traveling. If you change all these symbols to rotational quantities, you'll get these same formulas will become rotational formulas. So instead of v, we have omega for how fast something is spinning. The faster it spins, the higher omega is. So that's a Greek letter out of the Greek alphabet. That's now velocity. And instead of x, how far something moves in meters, we have how far it moves in a rotational sense, theta. Okay, so the velocity is the derivative of theta with respect to time, or if you want the average velocity, you just do delta theta over t, just like delta x over t. The units for linear motion, meters per second, the velocity. With rotation, the units are radians per second. But I put that in quotes because technically a radian is not a unit, okay? It's technically a unitless quantity, so the true units of omega are just 1 over seconds. But you're welcome to say and write radians per second. It's not going to be marked wrong. In fact, that's more often done even on AP tests to include the radian unit even though it doesn't exist. Okay, going on to acceleration, it's the derivative of velocity with respect to time, or delta v over t, and then the units meters per second squared. So we need a new symbol for the rotational acceleration, which is alpha, a Greek letter, and then we have the change in velocity, which is omega with respect to time, or instead of delta v over t, delta omega over t, and the units instead of meters per second squared, radians per second squared. Now you can relate the angular and linear quantities by just taking the linear quantities and dividing by the radius. If I turn this, and you imagine a point on the rim right here, where my finger is, I turn it through pi over 2 radians. I could figure out from how far that went, or I could figure out, say, how far it went by plugging in pi over 2 here in the radius of this lid, and I would get the arc length. Or as I'm spinning this, if I know the velocity of something going around in a circle, I could divide by the radius, and I get the omega, the radians per second. Same thing with the linear acceleration divided by radius, you get alpha. So they are related, these A's and alphas and V's and omegas, through these formulas. Okay, important to realize that these formulas are only for constant acceleration, which I mentioned in the kinematics unit. If the acceleration is a variable or a function, then you cannot use these formulas. But if acceleration is a constant, just like a number, like 9.8 for example, you could figure out how far something goes from this formula. X equals x0 plus v0 t plus 1 half at squared. Once again, replace all the linear quantities, okay, with thetas. Any v with omega, any a with alpha, and you get the rotational equation. And then the math procedures for solving for unknowns is the same as if you use this formula. This formula, you should recognize it. The v's become omegas, so omega and omega 0. This is the final speed, the original speed at time 0, and then a becomes alpha. This is the final speed, original speed, omega, omega 0, original angular speed, alpha for A, and delta theta for delta X. So kinematics, pretty easy. You just do pretty much the same thing that you did in the linear case over here in rotation. However, it gets more complicated from here. So now we're going to move on to concepts like force, mass, and acceleration. So when it came to linear motion, all you needed to know was how hard you pushed or pulled something to determine its acceleration, okay? It was as simple as measuring the force and then putting that into A equals F net over M. But when it comes to rotation, the force is more complicated. The thing that makes rotation, it's torque, a Greek letter tau, RF sine theta, and the units are newtons times meters. Sine doesn't have any units, so Newton meters are the units of torque. Let me show you the logic behind that formula. So I've got a bolt here, and I want to turn that bolt. Okay, so it's, screwed into something, obviously. So I get a wrench, and I put it onto the bolt like this. Now, I need a torque. I need a turning force on this bolt here. So I've got to, first of all, push on the wrench. But I can't push on it anyway. Like, for example, if I push in this way, the wrench doesn't turn. Because I have R, F, so I have a radius right here. I have a force, but theta is 180 degrees. When I calculate that, I get torque 0. No turning if I push directly on a wrench like that. Pulling on a wrench doesn't work either, right? So that didn't turn the bolt because I have R and I have F in the same direction. So I plug in sine 0 instead of sine 180 and I still get 0 torque. The most effective way is to push 90 degrees to the radius like this. Okay, now when I push like that, you see that I am creating a turning force, a torque. R, F, sine 90 gives me the most torque. So it's more complicated than just how hard you're pulling. You need to know the radius of where you're pulling or pushing and also the angle between the two. So that's the concept of force. What makes something accelerate is a torque in rotation. Now, obviously, in Newton's laws, linear motion, what inhibits an acceleration is the inertia or the mass. And in the case of linear motion, it was as simple as just determining the mass as something the kilograms. In other words, if you're pushing a person on the skateboard, if they're standing, kneeling on the skateboard, have their arms out or tucked in close to their body, it does not affect the acceleration. All that matters is the mass, not how the person is standing or sitting or whatnot. When it comes to rotation, it matters the geometry of the mass. A person's rotational inertia changes as their arms go in and out or they crouch into a ball or stand straight up. The most basic formula for rotational inertia is mr squared. This is for the inertia of a point mass. If at the end of a stick you've got a mass, like a ball of mass here that's very small in dimensions of the radius, its inertia is mr squared. You need to remember that formula, that when you have a mass at the end of a stick that's a very small point mass like I have drawn here, its inertia is mr squared. So just like with torque and forces, this is more complicated. The more you move this mass out, the same mass, the same kilogram, the same object will have more inertia if you move it at a different, at a greater distance from the axle. The units are kilogram meters squared. So this is a formula you have to know for the AP. Another formula is the parallel axis theorem. If you know the inertia of something at its center of mass, maybe for a disk we learned it was 1/2 mr squared, and then you put a new axle, a distance h away from the old axle at the center of mass, the new inertia is greater because the mass now tends to be further from the axle than if you had the axle here. It's greater by amount of the whole mass of the entire disk times h squared, how far the old inertia plus this term, that's what the new inertia is, it's greater. Another thing you're responsible for is finding the inertia of a bar. Well, this isn't a uniform density, but a uniform density bar. You have to integrate. So let's suppose I drill a hole in this bar and it's uniform right here, and it's this is a quarter of the length of the bar from a quarter of the way from the end of the bar. Okay, so there's the new axle. What I'm integrating is basically mr squared. This term, m over L, is the kilograms per meter, and when I multiply by dx, a tiny slice of some part of the bar, I have kilograms per meter times the meters in that little slice is the amount of kilograms in the little slice of a bar. So what I have is m r squared for a little slice. And then if I add up all the m r squareds throughout the bar, I'll get the total inertia of the bar. That's what the integration is. So again, when I had this at a quarter of the distance away, so there's my axle, I would put in the x squared, the mass of the bar over the length of the bar. Maybe that's like, I don't know, 20 centimeters. I'll make up a number, 20 centimeters, 0.2 meters. And then my limits would be, well, if this is 20 centimeters, then maybe this is negative 15 to positive 5. So it'd be negative 0.15 meters to positive 0.05, and I'd integrate between those limits, and I would get the inertia of this bar if its axle's there. Okay, so that's another thing that you have to possibly do on the AP. Then we have all kinds of other shapes: spheres, solid spheres, hollow spheres, cylinders, and in all those instances, the inertia is always some fraction times mr squared. You don't have to remember all the other formulas that, like for example, for a solid disk, it's 1/2 mr squared, 1/2 here. You don't have to remember that. You just have to know that it's something mr squared. And then in example problems, if you actually need the inertia to solve the problem, the AP test will give the inertia to you, the formula for the inertia. So these are the ones you have to know and memorize, but not all the other shapes. Okay, finally, we have force, inertia. We can now talk about the acceleration. In the linear case, it's the force, more acceleration, more mass, less acceleration. So F net over m. Again, just like we did over here, you could translate this and replace the linear quantities with rotational quantities. So instead of A, we have alpha. Instead of F net, we now have torque. That's what goes up here. And instead of mass, we have inertia. So that's what goes down there. The same concept: more torque, more alpha, more acceleration. The more inertia, the less acceleration. We can also have kinetic energy when something moves, right? If I throw this like this, right? So while it was moving, it had 1/2 mv squared joules, kinetic energy for the velocity. Okay? But when something spins, right? So if I do that, and while it's spinning, it also has spinning or rotational kinetic energy. 1/2, instead of mass, we have I. Instead of V, we have omega. 1/2 I omega squared. Okay, and that unit is also in joules. I didn't bother writing it because it's the same unit. In collisions, when things collide into each other, right? So we go like this, right? We have a collision. So we have the momentum that something comes into the collision with mv. When something collides with a spinning collision, we can write its angular momentum. First we need a new symbol, capital L instead of P. And then we just replace m with inertia and v with omega. And the units of that, if you look at these units, are kilogram meters squared over second. Okay, so that's basically, those are the units of angular momentum. However, something could have angular momentum even though it's not spinning. It's just moving linearly. Remember in class I was standing on a rotating platform. I said, imagine a pitcher throws a fastball directly at my chest and I catch it. Boom. That will not make me spin because the baseball's force of impact will go straight into the axle of me standing on a rotating platform. But if the baseball is shot to the side and I stick my hand out and I'm standing on the platform here and I catch it, that baseball moving is going to hit me and cause me to rotate. So something moving with a velocity and no spinning has an angular momentum by mvr sine theta of whatever angle the radius and the force and the velocity make between each other. So this is it. These are all the ideas in the rotational unit. Okay? Even for the next review lesson, review video 7, I'm still going to be using these ideas. So these are all the ideas of the rotational unit. What I'm going to do now is I'm going to do 3 examples. Okay, 3 examples regarding acceleration, figuring out the acceleration of something. But before I go into the 3 examples, I just want to say something first. As I've said several times during these review videos, at this point in the curriculum, you shouldn't be thinking about details. Okay, you should be trying to grasp main ideas and main techniques on how to solve problems. Any problem that you've solved already, pretty much guaranteed will not be on the AP. It's the thought process that's on the AP. So what I want to do is I'm going to try and get you to focus on the thought processes I'm using in solving these problems. Details will undoubtedly be different. So don't focus on the specific details. And I'll guide you when we get there. So, first example. Okay. We've got a bar, mass m, length L, and inertia, see, right? Inertia of a bar through its end is 1/3 ml squared. That's in the textbook. I got that on that table that we have of all those inertias. You don't have to remember that. So this would be just like an AP problem. They'd have to give that to you. Or maybe that's the unknown you're solving for, and you could solve for it without memorizing 1/3 ml squared. Okay? Actually, you might have to integrate to it. That is something they could ask you to integrate to find that inertia 1/3 ml squared. But anyways, I gave it to you. And it has 2m at the end of it. And I'm going to we'll determine the initial acceleration, the omega when the bar reaches the horizontal. Okay? So, this is what I'm talking about here with this setup. I've got the bar up like this. Here's the axle, and it's at some angle with the vertical. Okay? So, to figure out the acceleration, alpha, okay, I covered it up, but alpha is torque net over inertia. So I need the torque and I need the inertia. First thing I decided to do was calculate the inertia. The inertia of the bar is 1/3 ml squared right here. And this is the inertia of this mass out here, which is mr squared, something you have to remember. It doesn't have to be given to you because you're expected to know that the inertia of a point mass, a distance r from the axle, is mr squared. So the m is actually 2m, and the radius is from here to there, which is just the length of the bar, mr squared. So I highlighted this because these are details, and so I don't want you to focus, well, how did he get 7/3? In fact, I was contemplating not even writing that, but then it would kind of inhibit me later for other calculations. Jot this down. Don't worry about the common denominator at all. But this you should be able to understand how I wrote this expression out. The inertia of the bar and the inertia of the mass at the end. Okay, so that's the inertia. Now, the torque net. So I have to add up the RF sine thetas. I drew the forces that generate the torque. There's the weight of the bar, which we put right at the center of the bar. I didn't really put it at the center. I think I'm a little off. Maybe it should be more around a little further up. But anyways, it's in the middle. And it's a weight of mg is the mass of the bar times 9.8 gives me the weight. I also have to think about what its radius is. So here's radius 0, the axle. This is half the bar up, so it's at radius L over 2. And this theta is the same as the theta between the radius and the force. So I got to think of all the RFs and the thetas for all the forces that generate torque. The weight out here also generates a torque because we have a radius of L and a force of 2 mg. And so I plug that in to my torque calculation. Once again, I highlighted this. You should focus not on this, but on this. How did I construct this equation? Oh, I forgot to mention, by the way, there are forces at the axle that I didn't draw. So if this were the AP test and it said, you know, draw the forces, I would have to draw the forces here. There are forces here at the axle. But I wanted to skip that to just focus on the acceleration part today, or on this example. So again, this is highlighted, this step. This is the radius of that force, the force, and then the sine theta right there. This is the torque of this force. It's at a radius of L. The force is 2 mg, and then sine theta. Found a common denominator. Again, don't worry about how I got 5/2, but eventually that's basic what I did. I just added these two together. Once I have the inertia and the torque net, I can now use Newton's second law for rotation. Alpha is torque net over inertia. I take the torque net, the inertia, and that's it. I highlighted this again. Just realize where these came from. Don't look at the details. I solved it, but again, I don't want you to focus on this. Just write that down because again, this is not going to come up on the AP, pretty much guaranteed. Something like it might, okay? Maybe you have 3M or something like that. So the details could change, but we just want to look at the main thought processes. All right, now, that's the acceleration, that's part A. Part B, what is the speed when the bar falls to the horizontal position? So this, if I let it go, it's going to fall and maybe hit like a tabletop with a certain omega. Okay, and now we're asking for that omega as it's falling down when it gets to the horizontal position. First point I want to make is you cannot use this formula. Maybe I should have highlighted this too. But this formula only works for constant acceleration. But the moment this starts tipping down, this angle changes. It gets closer to 90 degrees. And so the torque increases. The alpha increases as it's falling. So this only works if the alpha stays a constant numerical value. But it does not. Okay, so we cannot use these. These are only for constant accelerations. What I have to use is energy. That's the easiest thing to use. And what I need to think about is the energy before and the energy after, and set them equal to get to each other. That's conservation of energy. So what I realize is the bar is up off the table a certain height. That means the bar itself has gravitational energy. And so does the mass at the end. It has a height, it's got a mass, it's got a gravitational energy. So these are the energies before. After, when it swings down and hits the table, we don't have those anymore. What we have is rotational kinetic energy. And so I set the energies before, these two gravitational energies, equal to the final energy, the rotational kinetic energy. So this is the mgh of the two masses. So mgh, 1/2 I omega squared. This is, again, I highlighted. And basically, you should understand how this was constructed. Again, not necessarily these details, because that could change with the problem, but just the thought process. So the m out here is 2m times g, so mgh. The h here, if you look at this, I've got a triangle. Radius of L. Theta over here. This is the adjacent side. If I want to know that, I have to do Hypotenuse times cos theta gives me the adjacent side, the height. Same thing here, mgh, hypotenuse L over 2, cos theta gives me the height there. So mgh, and then the inertia, I'm recycling it from back here. And then I solve for omega. See here, I didn't even write it out. I don't even want you to focus on what the final answer is. Again, it's just the thought process. How do you make something like this? That's what you've got to study and be ready for, obviously, different variations. So that's the first example. 2 more examples I'm going to look at today. Okay. So the next one here is a ball on a hill. So ball of mass m, radius r, inertia, again, this you don't have to remember for, I think it's a solid sphere or something like that. I forget what kind of sphere it is, but that's the inertia of the ball given as 2/5 mr squared on an incline theta, a height h from the ground level. We want to determine the acceleration, the minimum coefficient for no slipping to occur, and then the speed at the bottom. So first thing, I didn't say draw a force diagram, but this is something that you will definitely be, might have to do. Force diagrams are a big part of the AP mechanics test and curriculum. When it comes to rotation, like the previous diagram, where the forces are matters, because that's what generates torque, is the location and the orientation. So I drew the ball very light in the incline so that I could emphasize the forces. The force of gravity in rotation, we once again, like the bar problem that was falling, we put it right at the center of the object, at the center of mass. mg. Again, I don't write mg as a label. It's a force of gravity. mg is the magnitude, but it's fg. The normal force on an incline prevents this from breaking through the surface. Maybe this is a board. So the board has integrity and it doesn't break because it pushes the ball with a normal force to prevent it from breaking through. That's perpendicular to the incline. And remember from Newton's laws, that's the adjacent side here, mg cos theta. That's what this is. Okay? But it's going right here. Again, it's at the point of where it's applied, which is the board touches the ball right here. That's where it's pushing the normal force. And then there's a friction in the backwards direction. When something rolls down a hill, instead of just sliding down like this, friction holds it back, and that's what makes it turn rather than just sliding down. The friction here pushes back to allow it to alpha to accelerate like this. Okay, so there are the 3 forces on ball rolling. Now, I took care to draw this shorter than the horizontal component here because the gravity horizontal component here is greater than the force of friction. That's why the ball accelerates down the hill rather than going up the hill. But again, you cannot draw components on an AP diagram. If you want to do it right off to the side here, you're welcome to, okay? But not on the actual diagram where you're getting graded. So that's the force diagram, just 3 forces. So we're going to proceed on and try and calculate the acceleration. That's what we're looking for. So we try ma equals F net. And a lot of times I prefer writing Newton's law this way because in rotation it's very common to have a system of equations. And the system of equations is easier to solve if you have ma equals F net and I alpha equals torque net. So ma is the mass of the ball times the acceleration. The forward force is this x component that I cannot draw on this diagram. It's the mg sine theta on a hill, down the hill. There's a forward force and then there's a backwards force, force of friction. There are actually 2 unknowns in this equation. There's acceleration and there's force of friction, okay? This is not mu f normal because it's static friction. And static friction is anything less than or equal to mu f normal. It's just strong enough to prevent these surfaces from slipping past each other. So 2 unknowns. I cannot solve this for acceleration. So I have to make another equation. And that's what happens with all these rolling down a hill problems. We get stuck because we don't know what that is. So we cannot solve for this. So we move on to I alpha equals torque net. The inertia is 2/5 mr squared. That was given to me. The alpha we always change as a over r so that we have the same acceleration variable in both equations. And the torque net. There are three forces here. Only one of them creates a torque. This gravity is at radius 0, so it makes 0 torque. 0 Fg sine whatever, doesn't matter. It's 0 torque by force of gravity. The normal force is at a radius, but the theta is 180 degrees. Radius this way, normal force that way, plug in RF sine 180, that generates also 0 torque. The only force that creates an angular acceleration is this one. It makes the disk spin like this, accelerate that way. So RF sine 90, the radius and the force are 90 degrees. So you're welcome to leave off the sine 90s when they appear. Just say RF, and you don't lose any credit. The R's all go away, and that leaves me 2/5 ma equals force of friction. So again, these are the two highlighted steps. Don't focus on necessarily the 2/5 or whatever. That will change problem to problem. But I alpha equals R force of friction is the basic main idea in creating one of the equations in these hill problems. The other thing that you do, I guess I should have highlighted this, is usually you add up the equations, the left sides, the 5/5 and 2/5, 7/5 ma, and then the right sides, when you add them, the force of friction goes away, leaving you just mg sine theta. So maybe we'll highlight the plus sign or something like that. But again, the details, don't worry whether it's 7/5 or 8/3 or something. That all changes depending on the inertia. But the setting up the equations and then adding them together, that's a main idea for acceleration down a hill problem. System of equations, add them to get acceleration. Moving on. We just solved. Again, this is a detail I don't want you to focus on. Just jot it down. Don't worry how it got, don't look too carefully. Don't invest much time into how that comes out. It comes from here. Okay, now the next thing, the minimum coefficient for no slipping to occur. If this hill is too slippery, the ball won't roll, it'll just go down the hill sliding. So the first thing that I need to do is find out what the force of friction is, and I could use this equation. 2/5 ma equals force of friction. That's all from this equation. And then recall that force of friction is mu F normal. At the point of slipping, the mu static F normal. So here's my mu. The normal force is mg cos theta, right here. This side of the force of gravity triangle. This side right there. And then I just solve for mu. I didn't highlight any of this because you know what? It's not as important as being able to set up the system of equations. Don't study this so much, study this. Okay, the last thing, the speed at the bottom. So what they told you is that the ball started at distance h from the ground. Oh, I didn't write it, but there's h. And we want to find the speed at the bottom. The easiest way to do this, we could do it with kinematics because the acceleration is actually constant, so we could use the v squared formula. The problem is we don't know the distance here. We could figure it out, but it's easier just to use energy conservation. What we have in the beginning is gravitational energy. What we have here is the 1/2 mv squared of this thing moving forward like this, right? So 1/2 mv squared, but we also have it spinning. So we have 1/2 I omega squared also. We have both kinds of kinetic energy. So that potential energy goes to translational and rotational kinetic energy. And so this again is a highlighted main idea. Here's the potential energy, mgh. This is the translational kinetic energy, 1/2 mv squared. This is 1/2 I omega squared. So understand the thoughts behind this. The rest is just algebra. Jot it down. Don't focus too much on the details. This is where you get, by the way, most of your points on the problem. This might be 1 point. This might be like getting to this point might be 3 points. You obviously want to know how to set this up. And even if you don't get that, you'll still be in the running for a 5 out of 5 on the AP. That's example 2. One more example that I want to do today. So here's example 3. Okay. This is a multi-body problem. What we have is a pulley of mass m, radius r, Inertia, again, right? So you don't have to remember these formulas. If you need it to solve the problem, it will be given to you within the problem. So there's the inertia of this pulley. We've got 4m on the right and m on the left. And we want to determine the acceleration. So this is similar to Atwood's machine in Newton's laws, but in Atwood's machine calculation, we assumed the pulley had no inertia or negligible inertia. Now the pulley's mass is significant enough, so we have to factor it in. It slows down the acceleration further. So we want to get that acceleration. We want to figure out the tensions in the strings, and we want to find this force at the axle. So first thing I did is I drew forces on the diagram. You may have to do this, right? So let's go over how I got all these forces. So the first set of forces are all the gravities on all the objects. This hanging mass on the left is m, so force of gravity mg. Again, you don't have to write mg. You just have to label for credit the force of gravity part, okay? There's 4mg because this has a 4m mass, so 4m times 9.8 gives me the gravity on this side mass right here. And then there's the pulley itself that has a mass of m, so it's got a weight of mg. Alright, so obviously what happens is this goes down and that rises. How is this going to accelerate upward? Well, it needs a force upward, which ultimately came indirectly through this going down. That upward force has to be greater than the force of gravity. I don't know what it is, but maybe it's like 1.1 mg or 2 mg. I don't know, but it's got to be greater than mg for this to accelerate up, which is what would happen. Where did that force come from? It came from the pulley. So Newton's third law applies that if the pulley pulls up with tension 1, this pulls the pulley down with tension 1. Action, reaction, that's why I highlighted them both orange. Okay. This goes down, but it goes down at a smaller acceleration than 9.8. And the reason why is because there's a drag on it of the system here, is the inertia of this and that. So that's held back with a certain tension. That tension has to be smaller than force of gravity, 4 mg. So maybe it's only 3 mg or 1.5 mg. Whatever it is, this has to be able to accelerate down, so it's got to be less than that. Where does that come from? It came from the pulley. So if pulley pulls mass up, mass pulls pulley down with the same number of newtons. Action and reaction. I highlighted them both the same color to emphasize they're the same magnitude. So this has to be more than mg, this has to be less than 4 mg, but this side has to have greater force than this side because the pulley has to accelerate in the clockwise direction. So this has to be a greater force than that one. So all those conditions are true. And as I said in the Newton's laws unit, you do want to try and draw the forces to show as much that you understand as much as possible. So you want to try and draw these to an approximate length that shows the concept, this being greater than that one, but less than that one. And these two are the same. And then these two are the same, but less than that one. Finally, the axle is supporting up, preventing this pulley from falling downward, because now we have 3 forces downward, so we have to have something balancing that. Alright, so there's the force diagram. To figure out the acceleration, we have to use Newton's second law. I'm going to start with a pulley. I alpha equals torque net. The inertia was given. The acceleration I always replace in the system of equations, or I shouldn't say always, because we never know what they could think of, but most of the time you replace it with A over R. Okay, and then the torques, these two forces do not create torque on this disc because they're at radius 0. But these two do. This is the forward torque. RF sine 90, which is 1, so I leave it off. This is the backwards torque, so I put a minus sign. RF, oops, I mislabeled this. Okay, let's fix that. Tension 1. Okay, sorry about that. So yeah, that's the formula is correct. RF sine 90. Okay, And I could simplify and factor out all the radii, and I get 1/2 ma T2 minus T1. But this is not important, even though it's boxed. The highlighting, again, this is where you have to make sure you understand the thought processes. Later in another problem, they might make it 2/3 mr squared or something, so the details will change. But I alpha equals torque net. Understand how that was generated so that when you're encountering another problem, you'll be able to generate your own equation here with that thought process. Okay, well, there are three unknowns here, acceleration and tensions. So we make a system, we make other equations for these two objects. We're going to use ma equals F net. Starting with this one, 4ma, that's ma, right? ma. And then the net force is the forward minus the backwards. Here's the forward force, that's the backward force. Forward minus backwards. Then we do ma equals F net for this object. ma equals forward force minus backwards force. So these are highlighted also. Understand the thought process, don't get focused on the details, but know where the details came from. Okay? And that's the important part of this problem. Force diagram and generating the equations. Now, moving on. So, what we do is the easiest way to solve these is we add up all the left sides and add up all the right sides. And in doing that, again, don't worry about this detail where the 11/2 came from, but it basically came calling this 8/2, this 2/2, and that 1/2, and you get 11/2 ma is the sum of all the left sides. Okay, oops, the left sides here. Okay, so, and then on the right side, what happens is that positive and negative tensions drop out, so all we're left with is 4mg minus 1mg, 3mg. So add up all the left sides, add up all the right sides, that's the next step, and then you solve for A. So that's what I want you to focus on, is the idea of that. None of this is highlighted. Basically, you're just plugging in the accelerations back into these two formulas to figure out what the tensions are. So in equation 3, I put ma equals F net T1 minus mg, and I solve and I get that. Again, don't worry about the details, but you're just plugging back in. Same with here. I'm using this equation, equation 2, ma equals the net force here, and I solve for T2. I just want to point out that the thoughts of the various sizes of the tensions follow what I was saying, that this has to be greater than 1 mg. It is greater than 1 mg, okay? But it has to be less than T2. It is less than T2, right? And T2 has to be less than force of gravity here, 4 mg. Yes, that is. 4 mg is 44/11. So this is smaller, okay? So it satisfies the requirements. The last thing is that this upward axial force is not the sum of the gravities, because these gravities don't act on the disk. What acts on the disks are the tensions, okay? So you have the gravity of the disk plus the two tensions. That's going to be balanced. The 3 downward forces are balanced by the 1 upward force, 3 downward. Again, not really highlighted. I would rather have you focus on these steps here. The rest are just details. Well, that's it for today's review video. So again, we did 3 examples, okay? A pulley problem, and kind of outwards machine kind of problem, something rolling down a hill. Both of these involve making system of equations, rotational, linear, 3 equations here. Here we had 2, one for linear, one for rotational, okay? So rolling down a hill. Then we had this example of a bar rotating down. We had to calculate inertia and torque net and use alpha equals torque net over inertia. Possibly a little energy conservation in there also. So that was another example we did. And we went over all the ideas today. So this is the heart, what you want to look at. You definitely want to get all this down, understand it before you go and review the examples again. So this, all of the rotational topic, all the ideas and equations that you're responsible for. We got kinematics for constant acceleration. Then we've got forces, but we have torques instead of forces. We've got inertia, mr squareds instead of masses. We've got alpha, Newton's second law. We've got rotational kinetic energy and angular momentum. All right, so I'll see you in the next review video where we will be analyzing collisions. So we've practiced all of this, and then I saved collisions for the last review video on rotation, angular momentum. All right, see you next time.